Okay, so in this video, we're going to go over exam 2 so that you have that for yourself so you can prepare for the final exam. So let me share my screen. All right, so hopefully you can see this and this is recording properly. So we're just going to go through this exam one problem at a time. Actually, let me see if I can do something better. I was going to write in the whiteboard, but why not just write on the actual exam? Okay, so hopefully I don't run out of room when I'm doing this. This works fine. All right, let's see. Okay, so let's begin. So a lot of people had problem with parts B and C. They seem to have forgotten the quotient rule. So you can't. A lot of people just, when they did parts B and C, they just differentiated the numerator and the denominator separately. They didn't use the quotient rule. So you have to make sure that you're using the quotient rule when you differentiate a fraction of continuous or differentiable functions. But first, let's just do part A. So we're just going to do this term-wise. We're going to just differentiate each term individually. So the derivative of 6x to the 6th is going to be by the power rule 6x to the 5th. Well, first of all, let me just rewrite this a little bit so it's easier to differentiate. So I'm going to rewrite this second term as x to the negative second power. So we're just going to have to apply the power rule 3 times actually. Okay, so now that gives us back to the derivative. So we have 6x to the 5th, and then we use the power rule here by bringing down this power to this -2. So and we'll multiply by the 2, so we get -4. And the power rule says now you have to subtract 1 from the power. Get that. This is x to the -3, and then now we'll do the power rule on this third term. So we bring this power down 4/3 x, and then we subtract 1 from the power. So 4/3 minus 1 will give you 1/3. And then finally, we take the derivative of e to the cosine x. So yeah, there's a lot of different answers for this, and it's not sure where some of them came from, but the proper derivative of this involves using chain rule. So we have e composed with e to the x composed with cosine x. So we have to differentiate the inside function, which is cosine, and the derivative of that is negative sine x. And then the derivative of e to the x, which is just e to the x evaluated at cosine x. So this will be times e to the x evaluated at cosine x. Kind of ran out of room there. So let me just rewrite this. So this, what I meant to write here is the following: negative sine x times e to the cosine x. So this product here, and that will be the proper derivative. So now let's move on to the next part. So for this one, we need the quotient rule. So the derivative of g to the x by the quotient rule will be as follows. I need to differentiate the numerator, so e to the x, but that's just e to the x, times the denominator, the function in the denominator, which is x squared minus 5x, minus the function in the numerator times the derivative of the function in the denominator, which is going to be 2x minus 5, and then all of that divided by the denominator squared. As I said, a lot of people just just differentiated the numerator and the denominator separately instead of using the quotient rule. So you have to make sure you use the quotient rule. And this is the final answer. You can just leave it like that. You don't have to simplify it. So for this, there's, I think most people got this right, but some people, you know, it's hard to reproduce what was going on, honestly, but some people, like, they wrote this as like they separated it like this. I don't know. And this is not right. And then they, you know, canceled this out to get x plus x, and I guess that would give you 2x. So I saw that, and or some variations of this, but you can't cancel in that way because it's not the case that ln of a plus b is, this is not in general equal to this. So you can't split things up like that. For this one, we have to remember that if you take the derivative of, say, ln of like k to the x, so a function k to the x, it's just, so we differentiate this. Oops. It's going to be k prime of x over k of x. So we're going to need that derivative. We're going to need that rule when we compute this derivative. And again, we need, I mean, we need a lot of rules. There's a lot of layers to both of these problems. There's quotient rule and chain rule and derivatives of various functions. But first we need to use the quotient rule. So the quotient rule says we take the derivative of the numerator. So the derivative of the numerator is the derivative of the inside function divided by the inside function. So the derivative of e to the x plus x is going to be e to the x plus 1. Let me just actually do this on the next line, since I don't have to simplify. I'm going to run out of room. So this derivative, so by the quotient rule, so I take the derivative of the numerator, and that's going to be e to the x plus 1 over e to the x plus x times the function in the denominator, so 2 plus 3 sine x, minus the function in the numerator times the derivative of the function in the denominator. So the derivative of 2 is 0, and then the derivative of sine x is cosine x times the 3. So it's going to be times 3 cosine x. And then that's all divided by the denominator squared. So make sure you remember the quotient rule, because that almost definitely and surely will come up on the final. All right, so what about the next one? So for this one, yeah, there's a lot of people there. Yeah, there's a lot of different answers. Most everyone got this right, but some people forgot to use product rule and chain rule. So when we differentiate this, we need to use the product rule and the chain rule. So I'm gonna, if we differentiate this, so let's start differentiating it. You got to use the product rule here for the x to the 5th times y. So the product rule says that the derivative of this first term right here is going to be 5x to the 4th times y plus x to the 5th times y prime. Now, so that's product rule. And again, we have to use the product rule for this middle term and the chain rule, because now we're imagining y is some function of x. We don't know exactly what kind of function of x it is, but we're imagining it's some function of x. It depends on x. It changes as x changes. So this is, so how we interpret the cosine y is that this is the cosine of some function of x. So we need chain rule. We have an inside function and an outside function. So when we differentiate this, we get, we just take the derivative of x, and that's just 1. So we get cosine y. And then we take, and then add x times the derivative of cosine y. So that's by the chain rule, it's going to be y prime. So that's the derivative of the inside function times the derivative of the outside function, which is negative sine evaluated at y. And now I'm going to carry this on to the second line. So now we take the derivative of e to the y plus 1. So again, This is chain rule. It's not just we're imagining y is some function of x, and so we have e to some function of x, and we need to use, that means we need to use the chain rule. So the chain rule says we take the derivative of the inside function, which is y plus 1, so that will give us y prime, times the derivative of the outside function, which is e to the x, but that's just e to the x still, evaluated at the inside function. And then that's gonna, so this is, so far we just computed the left-hand side. Now we're trying to compute the derivative of the right-hand side, and that's just gonna be 0, because the derivative of 1 is 0. A derivative of a constant is 0. So now what we wanna do is we wanna solve for y prime. So we have a y prime here, a y prime here, and a y prime here. So we're gonna factor out the y prime. So let's carry this over here. So we have y prime. So now what we'll have is we factor it out of here, we get an x to the 5th. Here we get negative x times sine y. And then here we get plus, actually this is a negative here from this negative. So this should be minus e to the y plus 1. And now, so that handles that term, and that term. So now we have this term, and I guess just this term. So now we're going to put those on the other side of this equation. We're going to subtract them from this side, from both sides of the equation. And so we'll get negative 5x to the 4th y minus cosine y. And now we can divide both sides by this right here. So we do that, we divide by that, we get negative 5x to the 4th times y minus cosine y divided by the thing I just bracketed off. So x to the 5th minus x times sine y minus e to the y plus 1. So that gives us the derivative of y through implicit differentiation. And now we're going to, and that solves the first part. So now we're going to go into the second part, and we want to find the tangent line. So remember, the derivative gives you the slope at the tangent line. So we're going to evaluate for or at x is equal to e plus 1 and y is equal to 0. So if we do that, we see that y prime, which is going to give us the slope, is equal to the following. So I plug in 0 here, so that kills that term. And then so I don't even have to plug in for x, because that term will just vanish. And then have minus cosine of 0, but minus cosine of 0 is just negative 1. So that gives us the numerator. So I didn't even have to worry about plugging e to e plus 1 in the numerator, because this first term vanishes because of this y is equal to 0. And then as I said, cosine of y, cosine of 0 is negative 1. So now I'm going to go to the denominator and plug in some terms. So so first of all, this middle term right here, x times sine y, that's going to be 0 because sine of 0 is 0. So I don't even need to plug x in there. And all I have to do is worry about this term and this term. So this term goes away when you plug in y is equal to 0. So here I get e plus 1 to the 5th, and then minus e. So I plug in 0 for y, so I just get e. So this is the slope. And then now I use the point slope formula to find the line. So the point slope formula says you take this point, if you have a point and you have a slope, you can uniquely determine the line. So it's going to be y minus the y, it's going to be y minus the y coordinate, but that's just 0, is equal to the slope. So negative 1 over e plus 1 to the 5th minus e. So times, so it's y is equal to the slope times x minus the x coordinate. And that's it. So that finishes that problem. All right, so for this one, this next one, a lot of people had trouble with this one too. They forgot to use chain rule. Yeah, so this is sort of an implicit differentiation problem. So you need to use chain rule. So in other words, V and L, so V is the volume, and L is the length of the side. These are functions of time. There's some function of time. We don't know. What we do know is we're told that the length increases at a rate of 2 centimeters per second. So in other words, we're told the derivative. So what we're given is that the derivative of L with respect to time is 2 centimeters per second. And we want to know how fast is the volume increasing when the volume is 8 cubic centimeters. So I gave you the formula, and this is a pretty easy formula for the volume of Q, but I gave you anyways. And so we can differentiate this function with respect to time. So now we're going to differentiate L cubed. So we need to use the power rule with the chain rule. So L is some function of time. So let me just write this step out. So we're going to differentiate L cubed. When you do that, you got to use the power rule. So you bring down the power, and then you take the derivative of the inside function, which is L. So that gives you dL dt, and that's times L squared. You'd reduce the power by 1. So we can just write this as 3L squared dL dt. So now when V is 8 cubic centimeters, we can use this formula right here to find out what L is. You just take L is going to be L cubed will be 8 cubic centimeters. So that means if you take the cube root, L has to be 2 centimeters. And then we can now just plug that into this formula here to find the rate at which the volume is changing. So the rate at which the volume is changing is going to be 3 times L. Sorry. 3 times L. So L is 2 centimeters squared times dL dt, but dL dt is 2 centimeters per second. So times 2 centimeters per second. So now you square the 2 to get a 4. 4 times 3 is 12. 12 times 2 is 24. And then you have centimeter squared times centimeters, so that gives you the cubic centimeters over a second. So this actually represents a volume. So the cubic centimeters gives you the volume measurement. So this actually represents the rate at which the volume changes. So if you go into physics, it's important that you keep track of units in the way that I did. They'll get on your case about that, your physics professors. I mean, for me, it's like if you drop it here or there, I don't really care. As like if you got 24 at the end, but you just dropped units, like I gave you credit. But it's good to keep track of your units, especially if you go to study physics, because they're really, really, really particular about their units. So let's move on to the next one. So this one is one that a lot of people had trouble with. And honestly, this was a little harder than I should have made it. There's a couple of parts that are hard. So yeah, this is an important one to go over. Whoops, I don't know what I'm doing right now. Oh, okay. I don't know what happened there. Anyways, so hold on, I need to stop sharing for a second. And I will be right back. Okay, sorry about that. My dogs were going crazy, so I had to let them out. So let me share my screen again. Let's see. Okay, so here we are. So we left off at number 4. So we want to determine where it's increasing and decreasing, where it's concave up and concave down. So for that, we're going to need the first and the second derivative. So let's get the first derivative. So for this, we're going to need the quotient rule. And again, some people messed this up. I guess they forgot the quotient rule, or maybe forgot exactly how it went. But the quotient rule says that you take the derivative of the numerator, the function in the numerator. And so that's just going to be 1. Derivative of x minus 2 is just 1 times the function in the denominator minus the function in the numerator times the derivative of the function in the denominator, which is just 2x. And that's all divided by the denominator squared, which is x to the 4th. And then this simplifies. So yeah, if you do this out, you can see it's just going to simplify to negative x plus 4 over x to the 3rd. That's because you get this negative 2x to the x squared, and then you add an x to a square to that, so that gives you negative x squared. And then you have this negative cancels out this to give you 4x. And then the numerator and the denominator have a common factor of x. So you cancel that out. So that's why you get the x to the 3rd in the denominator, and then negative x plus 4. So for this, you're going to remember you need to, I guess you just need to do a little sign table. So you have, so we need to determine where the function, the derivative is positive and negative. So we need to use this sign table to determine that. And that's done by finding out where the function is 0 or where it's not defined. This will give us points where the sign of the derivative could possibly change. In other words, the critical values, the critical points. So the critical points are going to be 0 and x equals 4. So we have 0 and 4 here, and then we'll take some test points in each interval. So maybe we'll take -1 here, we'll take 1 here, and then we'll take x to the 5th here. And so this will give us, some columns. That's not that great. It's hard to draw with this pen. Anyways, whatever. This is, so we have to test the sign of x plus 1 or x plus 4, and then x to 3rd, and then this will give us the sign of the derivative. So when x is 1, this first expression will be, so this will be -5. So it's -1 will cancel with this negative to give me 5. So it's positive on this interval. And then of course x to the 3rd will be negative. So that means f prime of x is negative, sorry. On this interval, when x is 1, we get negative x plus 4 is positive still. X to the 3rd is positive, and so then the function f prime is positive overall. And then for this interval, when x is 5, the first expression is -1, so this is a negative. X to the 3rd will be positive, so this is negative. So this is decreasing, where it's decreasing. This is increasing, and then this is decreasing. So then we can summarize this as follows. We say f is increasing on the interval 0 to 4, and then f is decreasing on, so I'm going to write this on the second line because it's a union of two intervals actually. So negative infinity to 0, union 4 to infinity. Okay, so that's where it's increasing and decreasing. And now we need the second derivative to determine where it's concave up and concave down. So that is going to be the product rule again. So we're going to differentiate this expression right here. So we use, sorry, not the product rule, the quotient rule. So the derivative of the numerator is -1 times the function in the denominator. So that's negative x cubed minus the function in the numerator times the derivative of the denominator, which is going to be 3x squared. And then the denominator squared. And again, I'm not going to go through all this steps, but you can simplify this and you get, if you simplify this, you FOIL and then combine and cancel some common factors, you get 2 to the x minus 6 over x to the 4th. So now again, remember concavity, the second derivative test tells us about concavity. It tells us that when second derivative is positive, that corresponds to the function being concave up, and when the function is negative, the second derivative is negative, that corresponds to the function being concave down. And you notice this in this function, in the second derivative, we have this x to the 4th. So this term does not contribute to the sign of the second derivative, because this will always be positive. So we can just say doesn't contribute to the sign. So ignore it. So we can ignore it. So the sign is going to be completely determined by the sign of the second derivative is going to be completely determined by the numerator. But the 2 is always just positive. It's positive 2. So all we care about is the x minus 6. So from this decomposition right here, we can see that f is concave up when x minus 6 is positive, which is to say that x is greater than 6, which is to say that x is in the interval, x is inside the interval 6 to infinity. And then f is concave down when x minus 6 is negative, because that will mean that the second derivative is negative. And that is, of course, to say that x is less than 6, which is to say that x is in the interval negative infinity to negative, sorry, not negative 6, just 6. And that finishes the problem there. So for this one, I think people just remembered the problem on the review sheet and kind of just went through the steps and then said that this was eventually just infinity. So I changed it a little bit so that the answer is not infinity as it was for the similar problem on the review sheet. In this case, the answer is actually 0. So I changed it just slightly. I think you had to use one less application of L'Hopital's rule. So I made it just one degree less complex, I guess. Not sure if that's the proper way of saying things. But anyways, for this, you're gonna, as I said, use L'Hopital's rule. Apparently this was pretty generous, because when I told people about the exam, most were like, oh, I didn't even tell them when to use L'Hopital's rule. I just gave them a limit and let them leave it up to them to decide. So, but I don't like to be like that. I don't like to leave things up for guessing like that, especially when we're first learning things. I just make it clear what technique we're supposed to use. So we need to use L'Hopital's rule. And why are we allowed to use L'Hopital's rule? Well, as x goes to infinity, e to the x goes to infinity, x squared goes to infinity, and this product right here goes to infinity. So overall, we have infinity over infinity. So we can legitimately use L'Hopital's rule. So L'Hopital's rule says that if we have such an indeterminate form, infinity over infinity or 0 over 0, we can just differentiate the numerator and denominator separately and try to evaluate the integral, or try to evaluate the limit at that point. So some people, they got the derivative of e to the x wrong. They just said it was e. I'm not sure why that was the case, but that's not right. The derivative of e to the x is perhaps the simplest derivative. It's just e to the x. The derivative of e to the x is just e to the x. It's what you would say is a fixed point for the derivative operator. It's a fixed point. Applying L'Hopital's rule, we see that we get e to the x in the numerator because that's the derivative of e to the x, and then in the denominator we had to use the product rule on the second term. So we get 2 to the x for the first term, and then the product rule says that we get e to the x plus x e to the x. And so now every time you apply L'Hopital's rule, it's a good idea to try to evaluate the limit at each step to see whether or not you need to use it, or if you can just actually get a concrete number for the limit. And we see that if we take the limit as x goes to infinity, e to the x goes to infinity, 2 to the x goes to infinity, this e to the x goes to infinity, and this product goes to infinity. So we have infinity over infinity. So we need to apply L'Hopital's rule again, which is why I said that there's this possibility that you have to apply it multiple times. I didn't say exactly how many, but it said, you know, you would have to possibly apply it multiple times. So now we're going to do L'Hopital's rule again, which says that you just differentiate. To compute this limit, you just differentiate the numerator and the denominator separately. Some people did quotient rule, which is not right. So now that's the derivative of the numerator. So the derivative of the denominator is just going to be 2. So the derivative of 2x is just x plus e to the x. And then now we do product rule right here. So we get e to the x plus x e to the x. And again, if you try to evaluate this limit, you're going to get infinity over infinity. So we need to do L'Hopital's rule once more, and I think pretty certain that this is the last time. So the derivative of the numerator is e to the x. The derivative of the denominator, so this 2 is going to go away, and the derivative of e to the x is e to the x. So we took the derivative of that, and then the derivative of that term is just also e to the x. And for this, we need quotient rule one last time. Product rule. So the derivative of that will be e to the x plus x e to the x. And now notice the numerator and the denominator have a common factor of e to the x. So if you wanted, you could factor out e to the x in the denominator, and you'll have e to the, let me just write it. I'm afraid I'm going to run out of room, but let me see if I can squeeze it in anyways. So you can factor out e to the x. So each term in the denominator has a factor of e to the x. So this will become 1. This will become a 1. After factoring, this will become a 1, and this will become a 1. So you add those together, you get 3. And then this is just going to become x after you factor. And then now you can cancel e to the x, and you get 1 over 3 plus e to the x. So from going from here to here, we didn't apply L'Hopital's rule. We just simplified. So we applied L'Hopital's rule here and here and here at this stage. So 3 times. But now we're here, and so again, we just try to evaluate this limit to see whether or not we need to use L'Hopital's rule. But in this case, we don't, because as x goes to infinity, this thing right here goes to 0. And there's, I guess, a lot of different ways you can see this. You can think, you know, if you take, I mean, basically as x goes to infinity, this 3 just becomes negligible. If you take a billion and then add 3, you're not really enlarging the number that much. So really what we're dealing is the limit of 1 over x. You can sort of ignore the 3. And we know that the limit of 1 over x as x goes to infinity is infinity. And you can also just see that by graphing this also. You can try to graph this over here. It's pretty terrible, but oops. So 1 over 3 plus x is going to be 1 over x shifted to the left 3 units. So so we have this asymptote goes over 3 units. And then the graph of it looks something like this. And this is the graph of 1 over 3 plus 1 over 3 plus x. So you can see that as x goes to infinity, marches out to infinity, the graph is getting closer to 0. So really, I mean, these, so that's one way to see why this limit is 0. Another way is just to say that, as I said, 3 barely contributes anything. So this limit is comparable, the limit of 1 over 3 to the x is comparable to the limit of 1 over x. And we know that that goes to 0. So let's move on to the next problem. So this one is about anti-differentiation, and we have an initial condition. So when we anti-differentiate, you're going to pick up a constant because the antiderivative of a function is not unique. There are multiple antiderivatives. There are infinitely many antiderivatives. In fact, if you have one, if you have one antiderivative, you have infinitely many antiderivatives. But if you're given an initial condition, as we are, you can actually find one function that is antiderivative satisfying this condition. There will be a unique antiderivative. Before we can determine that unique antiderivative, though, let's just determine the antiderivatives. So for this, we need to use, we're going to have to use a couple rules. We need to use the product rule in reverse on these factors and on this, and then we have to remember what the antiderivative of cosine is. So let's just go one time. We'll go down the line one at a time. So for this, you use that power rule in reverse, which says that you add 1 to the power and then divide by that power. And then the next one is 2 times x, and we do the power rule on this term. So you add 1 to the power, so you have 1, so it becomes 2 over 2. And then the antiderivative, so remember that an antiderivative is a function such that when you differentiate it, you get the function that you started with. So we need to ask ourselves, what's a function such that when you differentiate it, you get sine x? Well, that's just cosine. Well, in particular, we want to put the negative with the sine x, because we know that the derivative of cosine x is negative sine x. So the antiderivative of this piece will just be cosine x, and then the antiderivative of 5 will just be 5x, and then of course this is where you add the constant. So we can cancel some stuff a little bit. So this will be x to the 4th over 4, and now cancel the 4, so we have just x to the 4th. And then we have these 2's that cancel out, so we have x squared plus cosine x plus 5x plus c. So some people had they maybe got to this step, but they didn't know what to do. Some people just said that c is equal to -1, but those aren't right. Some people had problem plugging in the function, evaluating the function here. So what this means is that when you plug 0 into the function, you're going to get -1. So if I plug 0 into the function, I get -1. But what happens when you plug 0 into the function? So this becomes 0, this becomes 0, this becomes 0, and then we have cosine of 0 plus c. Well, cosine of 0 is just 1. So what we have then is that 1 plus c is equal to -1. And then I can solve for c to get that c is equal to -2. And then you can say that, let's see, f of x is equal to x to the 4th plus x squared plus cosine x plus 5x minus 2. And that will be the answer. So for this bonus question, there are a few people that got this right. And then some people attempted it, and I gave, maybe a little bit of credit, but I didn't give you the full bonus, but I gave you something for trying. So for this one, a lot of people didn't use logarithmic differentiation. They just tried maybe quotient rule. And that is going to be it's not going to be as nice if you do quotient rule. It's possible to do it, but it's not as nice. So what we want to do is use, because there's going to be a quotient rule mixed with the product rule and the chain rule, and it just gets really messy. So we want to use the logarithmic differentiation, which involves taking the natural log of both sides. Of the expression or the function or whatever you want to call it. This is a 5 here. And now we're going to use the properties of the logarithm. So now we have a quotient. So that means, so remember, if you have a quotient, if you have the log of a over b, that's the log of a minus the log of b. And if you have a product, log of a times log of a ab, it's going to be log of a plus log of, well, crap, I run out of room. Let me start that over. So this is how you deal, this first line is how you deal with logarithms of quotients, but then we have the logarithm of a times b becomes the logarithm of a plus the logarithm of b. So I have division right here. So I'm going to split that using this first rule. So I get ln of x squared times x cubed minus 5 to the 5th. Oh, no, I'm sorry. This is a 2. And then minus the natural log of x squared plus 6 to the 4th. And I forgot there's actually one more rule we're going to need. It's the natural log. If you have the natural log of a to the nth power, you can bring the n down as a coefficient like this. So times. So n times the natural log of a. So now we're going to use this second rule to split this as a sum. So this will become ln of y is equal to ln of x squared plus ln of x cubed minus 2 to the 5th power minus ln of x squared plus 6 to the 4th power. Now I'll use the third rule, this power rule right here. Not the power rule in terms of derivatives, but this power rule for natural log function or just logarithm function. So this first term will become 2 ln x plus 5 ln of x cubed minus 2 minus 4 ln of x squared plus 6. And now you're going to need to know the derivative of natural log. So we're going to differentiate at this point. So we wrote that above, I think, somewhere. Let's see. Yeah, right here. The derivative of ln of kx is k prime x over kx. So when we differentiate this, we're sort of doing implicit differentiation here, actually. So this, the derivative of the right-hand side, our left-hand side is going to be y prime over y. And then the derivative of ln x is just 1 over x, so we get 2 over x. And then the derivative of this is going to be 5 times the derivative of x cubed minus 2, which is 3x squared. So this, I'll just write this as 15x squared over x cubed minus 2. And now we take the derivative of this. So it's going to be 4 times the derivative of x squared plus 6 over x squared plus 6. So the derivative of x squared plus 6 is 2x, and then we have the 4, so that gives us 8x over x squared plus 6. And then we can multiply both sides by y. So we get y times 2 over x plus 15 x squared over x cubed minus 2 minus 8x over x squared plus 6. And then you can substitute in for y because we know y is equal to this right here. So y prime is going to be equal to x squared times x cubed minus 2 to the 5th over x squared plus 6 to the 4th power times everything in the parentheses, 2 over x plus 15 over x squared over x cubed minus 2, it's supposed to be a 2, minus 8x over x squared plus 6. And as I said, that's the end. So this is the end. And if you do have questions, don't hesitate to email me about any questions you have. And I will be having office hours tomorrow. I'll either be more than likely, I'll probably be virtual because I still haven't. There was like no tests available today, so I'm gonna go get a test tomorrow. So I'll probably just do virtual office hours, and during the virtual office hours, we can go over this video or the solutions to this second exam, and we can also go over those 4 review packets. All right, so let's stop sharing.